Alright, we're ready to start section 6 of the review chapter on complex numbers and more quadratic equations. What we have here is an introduction to a new set of numbers, because everything we've done up to this point has been a real number. From even the solutions to the equations in the last sections. And the real numbers are the ones that we work with predominantly, but in pre-calculus and in calculus we'll also work with a set of numbers known as the imaginary numbers. I remember many years ago when I was teaching at, in a particular classroom, I asked the student if it wasn't a real number, what was it? And he raised his hand, he said it was a fake number. Well, close. An imaginary number, it goes as far back as the ancient Greeks with Heron back in Alexandria, and then the Italian Cardano in the, I think, the 1500s, maybe the 1600s for Bombelli, who gave us most of the operations. But everything is based on what we call the imaginary unit, I, which we define as the square root of -1. Now, we've not been taking square roots of negative numbers. We said not a real number. And it's not a real number. It's an imaginary number. And we use I to represent this expression. So that means if b is greater than 0, any positive number, the square root of the opposite of b would be I, the square root of b. Because remember from our properties before, if we have a product, this was equal to the square root of the product of the square roots. And of course that's I, and that's the square root of b. So what we're going to do in these next examples is we're going to simplify each one of these expressions, write our answer in terms of I. Now this is a fairly straightforward one, because we know 81, the square root of 81 is 9, the square root of -1. I'm going to do this one more time here. I'm going to write this as the square root of 81 times -1, which is the square root of 81, times the square root of -1, which is 9i. This square root of 81 is 9, the square root of -1, we defined it as I. Now in this problem here, I'm looking at this, and this simplifies, because 50, although not a perfect square, has a perfect square factor. So maybe one more time here. I'm going to break this down to 25 times 2 times -1. The square root of 25 times the square root of 2 times the square root of -1. The square root of 25 is 5. Square root of 2 is just the square root of 2, and the square root of -1 is I. Now, I'm not a big fan of putting the I after a radical, because sometimes the radical sign, the little top here, is written in hurry, and sometimes it looks like it overlaps and puts the I underneath. So most times I will write this as 5i, the square root of 2. It represents the same thing because multiplication is commutative. So this property, which I just used a couple, 3 times, this property is a good property for us to use unless we have both a and b negative. So one more example here. This is 11 times -1, so using this guy right here, this would be I, the square root of 11. So back to here. Let's say both of our radicands are negative, like in the example here. Can I use this property? Well, if I can use this property, the square root of -4 times the square root of -9 is the square root of 36, which we know is 6. Is this true? Well, according to what I just wrote down here, this would be the square root of 4 times -1, or 2i. This would be the square root of 9 times -1, which would be 3i. And if I multiply these together, 2 times 3 is 6, but I have I times I. I times I squared. Now what would I squared be? Well, if I is the square root of -1, I squared would be -1. So this becomes 6 times -1. This is -6. Not the same thing. So that's why both a and b cannot be negative if you want to use this property. This is false over here. This is a really important thing to remember. Powers of I to the first power is the square root of -1, or just I to the second power is -1. Well, what about other higher powers of I? So I have I to the first is I to the second, I just showed you that, was -1. What about I to the third power? Well, if I use my properties of exponents, I to the third power is I to the second power times I. And I to the second power, I just said, was -1, so this is -1 times I, or negative I, or the opposite of I if you prefer. I to the fourth power, well, that's I squared times I squared, which would be negative 1 times negative 1, which is a positive 1. So for my first four powers, I get four different answers, but you're going to see a pattern. I to the fifth power is I to the fourth power times I. And I just said that I to the fourth power is 1, so this is 1 times I, or I. I to the sixth, that would be I to the fourth power times I squared, which is 1 times negative 1, which is negative 1. I to the seventh is I to the fourth power times I to the third, which is 1 times I to the third is negative I, so that's negative I. And I to the eighth power, well, that's I to the fourth times I to the fourth, which is 1 times 1, which is 1. Note here, you're repeating values. I to the first power is I to the fifth power is I to the second power is negative 1, I to the sixth power is negative 1. I to the third power was negative I to the seventh power is negative I. I to the fourth power was 1, I to the eighth power is 1. The pattern's repeating every 4. So what happens is we can use that to our advantage. If I wanted I to the ninth, if I follow the pattern, it's I. I to the 10th, it'd be negative 1. I to the 11th, it'd be negative I. Well, that's all good and said unless you have a really big power of I to the 100th power, or 200th power, or 3,475th power. Then we still can use the pattern, but we're not going to go through them one by one by one. We're going to use the fact that if the exponent for I is a multiple of 4, that it's equal to 1. So let me go over to here. I to the 11th power is I to the 8th power times I to the third. And this is a multiple of 4. So this is 1. And I to the third power is negative I, so I get negative I. You really need to remember these 4 and then this pattern. Now I to the negative 103rd power, I have a negative exponent. I don't have to rewrite this with a positive exponent. I could, but I'm going to instead write this as I to the negative 104th power times I to the first. This is a multiple of 4. Okay? Because this is a multiple of 4, I can think of this as I to the fourth to the negative 26. And of course, I to the first is just I. This is 1. 1 to any power. This right here is 1. 1 to any power is just 1, so it's 1 times I, or just I. This one's really nice because 64 is a multiple of 4. So this is I to the fourth to the 16th. I don't even have to write that. I know if it's a multiple of 4 that this is equal to 1. Over here, another one with a negative exponent. I'm going to rewrite this. Now, I want a multiple of 4, but I don't want a multiple of 4 bigger than negative 30. I want to find the largest multiple of 4 that's less than negative 30. So I'm thinking I to the negative 32 times I to the second power. Remember back here, I broke this one down to negative 104 times 1. It wasn't just by happen chance. That is the largest multiple of 4 that's smaller than that exponent. So that's the same process here. This is just 1. And of course, I to the second power is negative 1. So this is negative 1. I can find any power that way, any integral power of I, using this pattern. Now, the imaginary numbers are a set of numbers different than the reals. But if you combine the real numbers and if you combine with it the imaginary numbers, you have what we call the complex numbers. A complex number is any number that can be written in this form. Notice the a plus bi, where a and b are real numbers. So the complex numbers contain all the real numbers and they contain all the imaginary numbers. You say, well, how do they contain all the reals? Well, they contain all the reals if b is 0. Because then the a is just a real number. Okay? If b is not 0, then you have an imaginary number. If b is not 0. Now, if a is 0 and b is not 0, then you have something maybe like 3i, or 0 plus 3i, which is 3i. This is referred to as a pure imaginary because there's no real value part. A plus bi, the a is the real part, the b is the imaginary part because it's times the I. Now these two symbols here, I've seen this symbol many times. This symbol represents the set of all complex numbers. Not as often do I see this where it looks like a capital I with an extra little slash in there. In this textbook, they call this the set of imaginary numbers. So the set of complex numbers is made up of the real numbers and, if I can draw it here, the imaginary numbers. Looks almost like a Roman numeral 2 there. I think one of these is supposed to be a little thicker, something like that. All right, now what we're going to do is we're going to take these three examples and we're going to identify these by the type of number. Is it a real number? Is it an imaginary number? Is it a pure imaginary number? Well, this is a real number. There's no I. It's just -3, real number. This has an I, a part of it. It has a 7 times the I, -7 times the I. So by definition, this is an imaginary number. This is also an imaginary number, but because there's no real part, the real part is 0, this is referred to as a pure imaginary number. So what we want to be able to do with this is we want to be able to perform operations involving imaginary numbers.